Always, sometimes, or never. If we let A and B be matrices, if we look at the product of A times B and then take the transpose of it, do we get B transpose times A transpose? Always, sometimes, or never? Well, I have already circled the always because it is always the case. Notice that if you take the product of A times B and then you transpose it, we have to be very careful that the order in which we do the multiplication, it is B transpose times A transpose. So we switch the order we multiply as well as taking the transpose of each one of them matrices. Well, let's prove that it's always true. I want to share with you one of the strategies that I like to use. There are many, many different ways we could prove this, but sometimes what I like to do is look at the entries in the corresponding matrices and show that they're equivalent. So the first thing I did was I said, let's let C be equal to A times B, and let D be equal to B transpose times A transpose. And what I wanted to do was to show that C transpose was equal to D. So what I wanted to do was to show that an entry in C transpose matched an entry in D. And I recall that if I look at the ijth entry in C, that is the jith entry in C transpose. So to prove this or show this, I need to show that for any I and j, the ijth entry in C matches the jith entry in D. So that's my strategy. So what I'm going to do is I'm going to let gamma I sub j be an ijth entry in C and show that it's equal to delta ji, which is the jith entry in D. So in order to do that, I'd like to play around on scratch paper first and describe what these entries might look like, and then I can come up with a formal proof. So what I did was I first looked at what the ijth entry in C might be. And I remembered from one of the homeworks that we did is we could find the ijth entry in any matrix by pre-multiplying by the transpose of a unit basis vector and post-multiplying by a unit basis vector. So if we wanted to find the entry in the ith row, we would pre-multiply by E sub I transpose. Jth column, we would post-multiply by E sub j. And again, from our homework, we know that this will give us the ijth entry in C. But C is equal to A times B, which means that this product is the same as the product E sub I transpose times the quantity A times B times E sub j. But what is this? Well, we know that matrix multiplication is associative and vectors are special matrices. So by associativity, we can regroup. And this is equivalent to E sub I transpose times A times B times E sub j. Well, the first product here is found by, well, it is the ith row of A. And the way we represent the ith row of A is by A sub I twiddle transpose. Okay, again, how do we know this? It's because the rows of A we represent, or the entries in the rows of A are often represented by A twiddles, and the sub I tells us it's the ith row that we're looking at, and the transpose tells us it's a row vector. Now when we multiply B times E sub j, we end up getting the jth column of B, which we usually denote by B sub j. And so that means that our entry gamma ij, which is just a scalar, is found by taking the dot product of the ith row in A times the jth column of B. But actually we knew that. That, in fact, was how we learned to multiply matrices in high school, if we do recall how we learned to do that. We take the ith row of A times the jth column of B to get the ijth entry of the product. So this isn't new. But if we now look at what the delta j ith entry is, that's the entry in matrix D that's in the jth row ith column, we can actually do the same process, and we end up writing it as the transpose of the jth unit basis vector times the matrix D times E sub I will give us the jith component. But D is B transpose times A transpose, which means that this product is exactly the same as this product. And again, by associativity, I can regroup. And so I can write it as the product of first the jth unit basis vector transpose times B transpose times A transpose times E sub I, the ith unit basis vector. Well, what will the results be? Well, if we look at this first product, this should give us the jth row of B transpose. Okay, what is the jth row of B transpose? Well, the jth row of B transpose is the same as the jth column of B itself. Well, the jth column of B itself we write as B sub j. But this is actually a row vector, so we're going to have to write it as B sub j transpose. So we know that it is a row vector. And what is this? This is the ith column of A transpose. But the ith column of A transpose is the same as the ith row of A. Well, how do we write the ith row of A? We write it as A twiddle sub I. But this is a column vector, so we don't need to represent it as, we don't write the transpose any longer. So what we've just found is the way to find the entry delta ji is we would take the dot product of the jth column of B with the ith row of A. Okay, where are we? If we compare delta ij, if we compare gamma ij with delta ji, this is the dot product of the ith row in A times the jth column in B. This is the dot product of the jth column in B times the ith row in A. Well, you know what? Dot product is commutative. So these are both scalars, and they give us the exact same result. So this dot product is equal to this dot product, which means that gamma ij, which is this dot product, is equal to this dot product, which was delta ji. So gamma ij must be delta ji. I can actually formally write this. Now let's go through a nice formal written argument for this. Again, I start with looking at delta sub ij, and I say that by our homework we could write it as the product of the transpose of the ith unit basis vector times c times the jth unit basis vector. And then I know that if c is equal to a times b, the following product is equivalent to the gamma sub ij. And this, by associativity, can be written as the product of the transpose of the ith unit basis vector with a times b times the jth unit basis vector. But that just means that the ijth entry in C is just found by taking the dot product of the ith row in A with the bth column of C. But since dot product is commutative, that's equivalent to taking the dot product of the jth row in B with the ith column in A. And then by property of unit basis vectors, I can write the bth column of J as actually, since it's a row vector, I can write it as the transpose of the jth unit basis vector with B transpose. Now, how did I get this? I'm actually working my way out from my description for delta ji. Here, I'm working my way backwards now. And I know that this is equal to this by just writing things as unit basis vectors. And then by associativity, that's equal to this. And then D is B transpose times A transpose. But then by our homework, if we're pre-multiplying by the transpose of the jth unit basis vector and post-multiplying by the ith unit basis vector, it's pulling out the jith entry of D, which is B transpose times A transpose. And so we have it done. We know that all of the entries in C, the ijth entry in C, matches the jith entry in D. So that means that C transpose is D transpose. So it is true that A times B quantity transpose is B transpose times A transpose. Again, my strategies here were to use scratch paper to describe each of these entries and then show that those entries were equal to one another. So this is a strategy I use often. Hopefully it helps you.